Continuing with the three laws of motion of Newton, we're now going to look at something called free body diagram. So the result of that is when we look at some mechanical situation, we need to understand how the three laws of motion affect the way we look at these situations. So our first example here is the one that same one as in our previous video. We have a person pushing against a wall, and what we're going to do here is we're going to isolate one single item on this diagram, in this case just the person itself. We're going to try and figure out all the forces acting on that person. So what we can do is we can use red to indicate the force acting on the person, and maybe blue for all the other forces that we may need to consider in order to help us figure out all the forces on the person. So first of all, the person has a mass and there's gravity, so there is a force pulling downward, F due to gravity, which is equal to the mass times acceleration due to gravity of the person. And of course, the reactionary force, Newton's third law tells us there's an equal and opposite reaction to that. So we can say that there's a force pushing back this way. So this is the force of the ground pushing back on the person. So that's the first force acting on the person. Secondly, the person is pushing against a wall. So we can say that, all right, person is pushing this way against the wall, and that means that Newton's third law tells us that we have an equal and opposite force of the wall pushing back on the person. So we have a force in this direction, and that's the second force acting on the person. And finally, the third force is that in order to be able to push on the wall, the person has to use their feet anchored on the ground to push backwards. So the person is pushing back this way against the ground, and then the ground, because of the friction between the feet and the ground, pushes back in this direction, a reactionary force like that. So we can see that in this particular case, as we consider this as a free body diagram, the person alone, there are three forces acting on that person. One from the ground up, one from the wall this way, and one from the ground in that direction. To differentiate between that in the next picture, here we have the person standing on roller skates, so there's not any possibility of forces acting in the horizontal direction between the feet and the ground. So what is going to happen here? Well, we can see that at the moment of the push, the person is going to push against the wall in this direction. The wall is going to have an equal and opposite reaction in the other direction. So momentarily, the wall is going to be pushing on the person. Of course, we still have the force of gravity, which means that we have the force of gravity downward. That's force of gravity, which is equal to m times g. And of course, we have what we call the normal force, the ground pushing back in the opposite direction. So that would be considered what we call the normal force. And this is the force of the wall pushing back. And then in this case, we stop. Now notice that if we only consider the forces acting on the person, you can see that there's a force acting upward, which cancels out with the force of the weight, so these are canceled out. Then we have the person pushing against the wall, which gets the reactionary force of the wall pushing back against the person. As long as the contact is made, what's going to happen here is that if we look at only the red forces here, you can see that the force of the wall is pushing against the person. There's nothing back over here to keep the person from rolling back, and so that means there's going to be, and let me use a different color for that, there's going to be therefore an acceleration in this direction as long as there's a contact made between the wall and the person. So for a momentary split second there, when the person pushes, the wall pushes back, the wall will push the person backward. There's nothing here to keep the person from going backward, and there will be a momentary acceleration. Okay, looking at this situation right here, we have something hanging from the ceiling. There's an object, it has mass m. Go ahead and just put an m in there. And so what are all the forces acting on this object? Well, in this case, we have the force of gravity pulling down. Gravity, which is equal to m times g. And now notice that if that was the only force acting on the object would accelerate downward. But there's a string here, or a rope on the other side, which keeps the object from coming down. So that means there is a force, a pull of the rope pulling upward. So F of the rope. And Newton's third law tells us that this would be equal in magnitude and opposite in direction to this force, so that these two cancel each other out. In other words, that causes there to be no acceleration. In this case, A is equal to 0. Then we look at this case right here. That's kind of a unique case. We have two objects on the ground. Let's say there's no friction between the objects and the ground. And we want to know what is the force on M1. What is the net force on M1? Now notice there's a force pushing both blocks and is of course going to accelerate both blocks to the right. If we take it as a whole system, we could then say, let's write that down. With using Newton's second law, we could say F is equal to M total times acceleration. So we can take a look at this as a whole system, and then we can say that the acceleration of both blocks is equal to the force on both blocks divided by the mass of both blocks. So just simply the mass of the first block plus the mass of the second block. So let me write the subscripts in. But what if I want to know the force only on M1? How do we do that? Well, let's go ahead and start with gravity. We have the force of gravity pulling the block down this way. So this is the force due to gravity, which is equal to M1G. Of course, then we have the normal force pushing back up. And so that would be the normal force going this way. And this normal force is the reactionary force to this force right here. It's going to be equal and opposite, and therefore they will cancel each other out. So there's not going to be any acceleration in this direction. But then we have the force pushing to the right. And so how do we figure out what portion of the force is actually acting on M1? So we're going to subtract the portion of the force that's acting on M2. So they're both accelerating with acceleration A to the right. So what we can say is that the force pushing on M1, there you go, let's call it F1. What is that going to be equal to? Well, that's going to be equal to F1 in magnitude is going to be equal to the total force pushing on both blocks minus the force needed to accelerate M2, which would be M2 times A. So if subtract this portion of the force from the total force, the remainder will be the force acting on M1. And of course, from Newton's second law, we know that F equals ma. So therefore, the force acting on M2 will be, and since I used the big M for M2, well, let's go ahead and keep that the same, big M. So therefore, the force apportioned to M2 will be the amount necessary to accelerate M2, and the remainder will be the force necessary to accelerate M1. So in essence, this will be equal to M1A. And that's how you want to look at forces acting on objects using free body diagrams and using the concepts of Newton's primarily second and third law. Newton's first law is used in different situations, but in this kind of situation, you mostly use Newton's second and third law to figure out how the forces are acting on objects and and if you want to isolate a single object within a situation like that, you can figure out how the forces act on that object alone by what we call drawing free body diagrams.